Welcome back to Mining of Massive Datasets. In the previous section, we studied the MapReduce model and how to solve some simple problems using MapReduce. In this section, we're going to go under the hood of a MapReduce system and understand how it actually works. Just to refresh your memory, a MapReduce system has a simple MapReduce process has 3 steps. In the map step, you take a big document which is divided into chunks, and you run a map process on each chunk. And the map process goes through each record in that chunk, and it outputs intermediate key value pairs for each record in that chunk. In the second step, which is a group by step, you group by key. You bring together all the values for the same key. And in the third step, which is a reduce step, you apply a reducer to each intermediate key value pair set, and you create a final output. Now, here's a schematic of how it actually works in a distributed system. The previous schematic was how it worked in a centralized system. In a distributed system, you actually have multiple nodes, and map and reduce tasks are running in parallel on multiple nodes. Here a few chunks of the file, input file, might be on node 1, a few chunks on node 2, and a few chunks on node 3, and you have map tasks running on each of those nodes, and producing intermediate key value pairs on each of those nodes. And once the intermediate key value pairs are produced, the underlying system, the MapReduce system, uses a partitioning function, which is just a hash function. So the MapReduce system applies a hash function to each intermediate key value, and the hash function will tell the MapReduce system which reduce node to send that key value pair to. Right? This ensures that all the same key values, whether they're in map task 1, 2, or 3, end up being sent to the same reduce task. Right? So in this case, the key K4, regardless of where it started from, whether in 1, 2, or 3, always ends up at reduce task 1, and the key K1 always ends up at reduce task 2. Now, once the reduce task has received input from all the map tasks, all the map tasks have completed, then you can start the reduce tasks. And the reduce task's first job is to sort its input and group it together by key. And so in this case, there are 3 values associated with the key K4. They're all grouped together. And once that is done, the reduce task then invokes the reduce function, which is provided by the programmer on each such group, and creates the final output. Okay. So remember, the programmer provides 2 functions, map and reduce, and specifies the input file. The MapReduce environment has to take care of a bunch of things. It takes care of partitioning the input data, scheduling the program's execution on a set of machines, figuring out where the map tasks run, where the reduce tasks run, and so on. It performs the intermediate group by step. And while all this is going on, some nodes may fail, and the environment makes sure that the node failures are hidden from the program. And finally, the MapReduce environment also manages all the required inter-machine communication. So we're going to take a look at exactly what's going on in a little bit. So let's look at the data flow that's associated with MapReduce. Now the input and the final output of a MapReduce program are stored on the distributed file system, and the scheduler tries to schedule the map task close to the physical storage location of the input data. Now, what that means is that, recall, the input data is a file, and the file is divided into chunks, and there are replicas of the chunks on different chunk servers. The MapReduce system tries to schedule each map task on a chunk server that holds a copy of the corresponding chunk. So there's no actual copy, data copy associated with the map step of the MapReduce program. Now, the intermediate results are actually not stored in the distributed file system, but stored in the local file system of the map and reduce workers. What are intermediate results? Intermediate results could be the output of a map step. An intermediate result could be something that's emitted while in the process of computing a reduce. Now, why are such intermediate results not stored in the distributed file system? It turns out that there is some overhead to storing data in the distributed file system. Remember, there are multiple replicas of the data that need to be made, and so there's a lot of copying and network shuffling involved in storing new data in the distributed file system. So whenever possible, intermediate results are actually stored in the local file system of the map and reduce workers instead of being stored in the distributed file system to avoid more network traffic. And finally, as you'll see in future examples, the output of a MapReduce task is often the input to another MapReduce task. Now, the master node takes care of all the coordination aspects of a MapReduce job. The master node keeps, associates a task status with each task. A task is either a map task or a reduce task. And each task has a status flag, and the status flag can either be idle, in progress, or completed. The master schedules idle tasks whenever workers become available. Whenever there is a free a node that's available for scheduling tasks, the master goes through its queue of idle tasks and schedules an idle task on that worker. When a map task completes, it sends the master the location and sizes of its the R intermediate files that it creates. Now, why R intermediate files? There's one intermediate file that's created for each reducer. Because the output of the mapper has to be shipped to each of the reducers depending on the key value. And so there are R intermediate files, one for each reducer. So when a map task completes, it stores the R intermediate files on its local file system, and it lets the master know what the names of those files are. The master pushes this information to the reducers. Once the reducers know that all the mappers map tasks are completed, then they copy the intermediate files from each of the map tasks, and then they can proceed with their work. Now, the master also periodically pings the workers to detect whether a worker has failed. And if a worker has failed, the master has to do something, and we're going to see what that something is. If a map worker fails, then all the map tasks that were scheduled on that map worker may have failed. So the tricky thing is that the output of a map task is written to the local file system of the map worker. So if a map worker fails, so then the node fails, then all the intermediate output created by all the map tasks that have run on that worker are lost. And so what the master does is that it resets to idle the status of every task that was either completed or in progress on that worker, right? And so all those tasks need to be eventually redone, and they will eventually be rescheduled on other workers in due course. If a reduce worker fails, on the other hand, only the in-progress tasks are set to idle. The tasks that have actually been completed by the reduce worker don't need to be set to idle, because the output of the reduce worker is the final output, and it's written to the distributed file system and not to the local file system of the reduce worker. Since the output is written to the distributed file system, the output is not lost even if the reduce worker fails. So only in-progress tasks need to be set to idle, while completed tasks don't need to be redone. Right? And so once again, the idle reduced tasks will be restarted on other workers eventually. What happens if the master fails? If the master node fails, then the MapReduce task is aborted, the client is notified, and the client can then do something like restarting the MapReduce task. So this is the one scenario where the task will have to be restarted from scratch, because the master is typically not replicated in the MapReduce system. Now, you might think that this is a big deal, that the master failure means that the MapReduce task is aborted and then the task has to be restarted. But remember, node failures are actually rather rare. A node fails, as you recall, once every 3 years or once every 1,000 days. And the master is a single node, and therefore the chance of a master failing is actually quite, it's quite an uncommon occurrence. The problem that you have is that when you have multiple workers associated in a MapReduce task, it's much more likely that one of many workers failed rather than the master failing. So the final question to think about is how many map and how many reduced jobs do we need? Right? Suppose suppose there are M map tasks and R reduced tasks. Our goal is to determine M and R. This is part of the input that's given to the MapReduce system to let it know how many tasks it needs to schedule. The rule of thumb is to make M much larger than the number of nodes in the cluster. You might think that it's sufficient to have one map task per node in the cluster. But in fact, the rule of thumb is to have one map task per DFS chunk. And the reason for this is simple. Imagine that there is one map task per node in the cluster. And during processing, the node fails. If a node fails, then that map task needs to be rescheduled on another node in the cluster when it becomes available. Now, since all the other nodes are processing, one of the map tasks has to, one of those nodes has to complete before this map task can be scheduled on that node, and so the entire computation is slowed down by the time it takes to complete this map task, redo the failed map task. So if instead of one map task on a given node, there are many small map tasks on a given node, and the node fails, then those map tasks can then be spread across all the available nodes. And so the entire task will complete much faster. On the other hand, the number of reducers R is usually smaller than M, and is usually even smaller than the total number of nodes in the system. And this is because the output file is spread across R nodes, where R is the number of reducers, and if it's usually convenient to have the output is spread across a small number of nodes rather than across a large number of nodes, and so usually R is set to a smaller value than M.